So this question is about halogenoalkanes in the upper atmosphere, chlorofluorocarbons and ozone. When you have a chemical like chlorine, or a chemical that's got chlorine in it, like a chlorofluorocarbon that's got a C to Cl, so it's got a chlorine atom in there, that covalent bond can break. It can break in the upper atmosphere in the presence of UV light. And the UV light provides some energy, and the pair of electrons in the C to Cl covalent bond, one electron goes back onto the C, and one electron goes back onto the Cl. So in other words, the share that they've set up is broken and they get their electron back. That creates a chlorine atom again. Instead of it being in a covalent bond with the Cl, it's reformed as an atom. Now the only difference is that we show the unbonded electron, the electron that was once in that bond, as a dot. It's an atom, so chlorine atom is sometimes called a radical. It's an atom that's reformed, it's an atom that was once in a covalent bond, and to show that it's got its electron back, we show that as a dot. It's called an unbonded electron, and it forms when that C to Cl bond breaks, or in some cases, if you've got chlorine itself, ClCl or Cl2, it's when Cl2 breaks or when CCl breaks. So a bond between a Cl and a C, or between a Cl and another Cl, when it breaks in the presence of UV light, the two atoms break the covalent bond and the atoms get their electron back, and you draw it as a Cl dot, which is a chlorine radical. That is its unbonded electron, the electron that was once in that covalent bond. But to all intents and purposes, it's a chlorine atom. If something's a Cl dot, then it's very reactive. And what actually happens is the Cl dot reacts with ozone. Now ozone is O3, you need to remember that, O3 for ozone, and it makes something. You can't remember this, but you can remember this, O2. O3 always makes O2. There's only two forms of oxygen, O3, ozone, and our sort of normal day-to-day oxygen that's in the atmosphere that we use for respiration is O2. Now you can work out what's left. So I've not used a Cl, there's 3 O's there, 2 O's there, so there must be an O and a dot. So you can always work this out even if you can't remember it. Now, which of these are going to react again? ClO dot is a radical with an unbonded electron, so that's going to react again. It reacts with more O3, so this ClO dot, this radical, reacts with more O3, and the only thing that it can make is O2. Now you can balance out the O's. I've got 4 on the left. I can balance it out by putting a 2 in front of the O2, and that means all the O's are now balanced. The only thing that I've got is a Cl and a dot. I've remade the chlorine radical. It's a catalyst. This is called a chain reaction where it goes on and on and on. The Cl dot is remade. It's a catalyst. That's why one Cl dot from a chlorofluorocarbon or from chlorine in the upper atmosphere in the presence of UV light, one chlorine radical can react with an awful lot of O3 and can cause holes in the ozone layer and some skin cancers. Chlorethane reacts with potassium hydroxide in the presence of propan-1 alpha-form ethene. So potassium hydroxide can do two things. It can either, in the presence of cold water, it can do something called nucleophilic substitution, and it can replace the Cl with an OH and make ethanol. But in this case, if it's making ethene, usually because it's in warm ethanol or warm ethanolic solution, it's called an elimination reaction. And the mechanism is actually this. It's a 3-arrow mechanism where the OH minus uses its lone pair to attack an H next on the C next to the C of the Cl. So if you find the Cl and trace it back, the Cl is joined to that C, which is joined to a neighbouring C, and it's one of these H's on the neighbouring C of the CCl that gets attacked. When that H reacts with an OH minus, it makes water, because this OH minus is giving electrons away to bond to the H. So now I've got H2O, and it's given electrons away, so it's lost its minus charge. The electrons from the H now, so this H is bonded with the OH, the electrons in that C to H bond move in between the two C's and form a double bond, and the Cl is broken off. The Cl is electronegative anyway. This is a polar bond with a slight delta minus charge on the Cl. It's electronegative, drawing electrons towards itself, and it breaks and goes onto the Cl. And because electrons are moved onto the Cl, that becomes Cl minus. So that's the mechanism that we're looking at, and it's elimination because this chloroethane has lost a Cl and it's lost an H, so it's had atoms eliminated from it. The role of the potassium hydroxide. So the role of potassium hydroxide, it's not a nucleophile. A nucleophile would attack that C there, that C with a delta plus, and eliminate the Cl, and it would form ethanol. So it's not a nucleophile. It's actually, if you have a look at it, OH minus becomes H2O. So it's gaining an H and it's losing the minus. It's actually gaining an H plus. Something that accepts an H plus is called a base. What's the role of the propan 1-ol? Well, the propan 1-ol doesn't appear here at all. So what's the role of the propan 1-ol? You might think it's a catalyst. It's a tricky question. It's actually not a catalyst. What it's actually doing is it's allowing these two chemicals to react together, because this chloroethane is not really soluble in water, and this is soluble in water, but they're both soluble in propan 1-ol. So it's a solvent. It's used to dissolve both chemicals to allow them to react together. A tricky question, that. It's allowing both of these chemicals to mix. Name and outline a mechanism for the reaction. Well, we've done that already. We've decided it's elimination and we've talked this one through. The structure of polymer A is shown below. Draw a structure of the monomer used to form polymer A. Well, I've got a backbone of carbon atoms here. So the backbone of carbon atoms means it's been addition. It's an addition polymer. It's formed from addition of unsaturated monomers, so short chain molecules with a double bond. And you've got to find the repeating unit. So if you find the repeating unit, the repeating monomer is this, CCFFFCl, and you can see that repeats itself 3 times here. So I find the short repeating unit, and the way that that's joined together is once upon a time it's had a double bond in between the two Cl's that has broken and formed a long chain.